For normal curves, they are bell-shaped curves, and the distribution of a normal curve is set up with what they call in the 68, 95, 99.7% rule. I threw in the 100% there at the bottom because all of the data is 100% of the data. Maybe I'll write that here. All of the data, 100%. Now 100% is not within 4 standard deviations. It's just everything that's left after we've counted up to the 99.7%. This curve is symmetrical. That means if you fold it in half, the two portions meet up perfectly. With that, regions D and E are going to be the same size. So if you take 68 and cut it in half, you get 34 and 34. Every normal curve, this is the percentages. And then to get C and F, I would have to say, well, wait, I've already counted 68%. So let's subtract 68% from 95 because areas C, D, E, F add to 95%. Subtract 68, you get 27. Divide 27 by 2. C and F are both 13.5%. 3 standard deviations. We have 99.7% of the data. Now, with the 2 standard deviations, we've already counted 95%. So we subtract 95 from 99.7. We get 4.7. That is 4.7% shared equally between B and G. So if you divide 4.7 by 2, we get 2.35. Regions A and H, across the board, A through H is 100% of the data. And I would call A and H the fringe. That's what students typically forget. The reason they forget it, if you look at the pictures, if drawn correctly, are just about touching the horizontal line. So it looks like you're done, but you are not done. The fringe on each side is 0.15% of the data. Those numbers you need to know, and typically after I've gone over them, a student will raise their hand and say, where'd you get those from? Basically, what I just said about where they came from, that's sufficient for this course. Mathematicians and statisticians have studied normal curves for years. They came up with these numbers, 68, 95, 99.7%. You do not need to know the statistics and the math behind how they got that. Just that they got that. And we'll use these numbers to work the problems in this section of the book.